Okay, in this video I want to discuss Green's theorem in the plane. Okay, let's go ahead and look at this, the conditions under which it holds and what it means here. Let R be a simply connected region of the plane with boundary del R. Okay, now simply connected, you can think of that in the plane as simply being the region has no holes in it. Okay. Online, I've give a more advanced definition that holds for all dimensions. But in the plane, just think about there's no holes in the region. Okay? And now I'm going to have this following vector field F. And it's going to be a function of points in the plane. So I've got my first function being m of xy and my second n of xy. So you can think of those as the components of I and j respectively. Okay? All right, this is going to be defined in an open region containing R. Okay? So it contains this simply connected region of the plane. M and n have continuous partial derivatives. These are for these integrals to exist that we're going to see here. Okay? Then the following is going to hold. If you take the line integral all the way around the boundary of R of m dx plus n dy, this is going to be identical to the double integral over R of the integrand n sub x minus m sub y dA. Now you can change the order in which you're going to integrate, which might be more convenient one way or the other. N sub x, m sub y, what are these? These are partial derivatives. You remember that subscript notation? So this really means the partial derivative of n with respect to x minus the partial derivative of m with respect to y. Okay? A more advanced way of looking at this is the following. Okay? This is equivalent to saying the following in the plane here. You're integrating around the boundary of R of f dot dr. Okay? Remember what f was. F was simply this field m n. Okay? And what's dr? Okay, that's a change in position vector. So you'd be dotting dx dy. Okay? And you can see if you can take the dot product of those two, right? You know how to do that. That you get what? That expression right there. Okay? Do you remember how to compute the curl with ijk? Okay? Right, if you actually go ahead and sit down and compute the curl of f, remember it only has what? These two components. So you imagine the k component being 0 and compute the curl in the usual way and dot that with k hat. What you'll end up is seeing that it's just exactly that expression right there. So some people like to remember it this way. Okay, so there's Green's theorem. Let's look at some examples of something like this. Suppose that I was going to integrate around the boundary of R 2y dx plus 3x dy, and I'm wondering what that would end up being. Now, what's my my region here? This is actually this rectangle, okay? X is between 0 and 1, y is between 0 and 1. Okay, so just think of that. It's actually not just a rectangle, it's a square, isn't it? Okay, so a type of rectangle. Now let's go ahead and see this here. What's playing the role of my m and what's playing the role of my n? So in the line integral, m will be the first one, so that'll be the component there on x. Okay, let's pull up here and see it. And my n is the component on y, so that's the 3x, okay? All right. Well, Green's theorem would say we can perform the double integration over n sub x minus m sub y. If I take the derivative of n with respect to x, I would get 3. If I take the derivative of m with respect to y, I would get 2, so I should get 3 minus 2 dA integrated over r. And that should be the same as that line integral up there, okay? All right. You can see 3 minus 2 is 1, so you're just actually finding the area of the circle, aren't you? Or the square, aren't you? So you're just finding the area of the square. I don't think we'll perform an integration there. I think we can all see a 1 by 1 square actually has an area of 1. Okay? 1 by 1. So the answer to this is what? That is actually equal to 1. Now that's going to be a lot easier way of actually computing this particular line integral rather than what? Going around the square and parameterizing each of the 4 edges. You could do it that way if you wanted, right? You could create the xy plane and, you know, between 0 and 1 here for each of these. And you could actually get, you know, that would be another way of checking it here. But this is clearly the easier way, okay? All right. Let's go ahead and try another one here. Let's say R is the unit circle centered at the origin with radius 1 that you can see there. This is actually the disk, I should say. Okay. Use Green's theorem to evaluate the following. Okay, the line integral around the boundary of that circle, x squared y dx minus xy squared dy. And I gave that a name, I just called it L. Okay, you can see that the m here, that's the component, or think of that as, yeah, the dx factor or coefficient there, which is functional. So that's going to be the x squared y, okay? We know we want m sub y, so right away I just jumped in there and took the derivative of that with respect to y, and you can see it's x squared. Okay, n, what would that be? Don't forget that's a negative sign in there, and the way we have it, m dx plus n dy. So we've got to have n being negative xy squared. Now, if we differentiate that with respect to x alone, you can see that we're going to get what? Taking that partial derivative, negative y squared. Okay? So, if I do this, okay, the double integral of n dx minus my, right? Using Green's theorem, m sub y, we would get what? Negative y squared minus x squared dA. Okay? Now, we're going around this unit circle, right? Or over this unit disk centered at the origin. So this is going to be pretty easy here. If you look at this, this is begging for what? This is begging for polar coordinates, okay? X squared plus y squared is r squared, so we really have what? Negative r squared. And then dA, right, differential area, when you're talking about polar coordinates, should be what? R dr d theta, okay? Now on the unit circle, we'd be going from what? 0 to 1, right, or the unit disk. And what? Theta would be going from 0 to 2 pi. So this is what our integral looks like. It's pretty easy to compute here. You can see just mentally we would have integrate first negative r cubed dr. So that would be negative 1/4 r to the 4th going from 0 to 1. Okay, going from 0 to 1 we would get negative 1/4. Okay, and then going theta goes from 0 to 2 pi, we would get negative 2 pi over 4 or negative pi halves. Okay, so let's double check here. Did I do that right? Negative 1, or negative r cubed, right? So that would be negative 1/4 r to the 4th. I hope I didn't get the sign wrong. That's to the 4th power. Going from what? 0 to 1. Okay. No, I got that right then. Okay. All right, looks good. I'm going to check by evaluating the line integral directly, just to show you that it's working here. Okay, now what we're going to do, remember here's the original question. We're trying to figure out what that guy was equal to. We figured out it was, what, negative pi halves. Okay, now I'm going to do this because we're integrating around the boundary of that disk. That is, that unit circle centered at the origin is the boundary, right? Okay, that's del of r. That's just their notation for boundary for some reason. Anyway, what we're going to do is parameterize that boundary, and then we'll go ahead and integrate directly, so we'll see what the value of L is that way. Okay, since it's a unit circle centered at the origin, we probably want to parameterize it this way, trigonometrically. So x is the cosine of theta, y is the sine, going between 0 and 2 pi, as you can see. Dx would be what? Negative sine theta d theta. Dy would be cosine theta d theta. Okay, now going back to what we had here, we actually had x squared y dx, okay, minus, right, x y squared dy, okay? So we just put all those values in there, okay? Or wrote those all in terms of theta. We're going all the way around this. Oh, wait. Oh, no, I did remember my d theta's there. Sorry, I thought I blew it just for a second there. Okay. Theta is going from 0 to 2 pi. Yes, so there's our L. Okay, so what do we get here? It looks like we get negative sine squared cosine squared in both cases. Or I guess I've written that cosine squared sine squared. Okay, so that's negative 2 cosine squared sine squared d theta. Okay. And do you remember that we have the following identity? That the sine of 2 theta is what? 2 cosine theta sine theta. Okay, so if I squared that and then took half of it, I would get precisely this quantity, 2 cosine squared sine squared. So I've written it that way instead. So it's negative, don't forget the negative out there, 1/2 sine squared of 2 theta d theta going still from 0 to 2 pi. Okay, you remember the formula for sine squared, 1 minus cosine, double the angle, so that would be 4 theta over 2, but then we've got this other 2, so that would give us a 4 down here, and that's what we're integrating. And you can see, well, when we integrate the cosine, we're going to get a sine from 0 to 2 pi, so that's going to disappear. So we're really looking at minus 1/4 theta going from 0 to 2 pi, and that's pi, negative pi over 2, just like we had before. Okay, so it worked. So the good deal. Okay? All right, let's look at maybe some more here. Let's look at this thing. Evaluate this, okay? Oh, by the way, you notice, I guess I should have been emphasizing this, I'm sorry. You notice that we're going in the positive direction, like most of our circulation integrals and stuff here. We're going around like this. See, it's the positive direction, meaning counterclockwise. Okay, I've got 2xy dx plus y squared dy, and I'm calling that L, okay? For L stands for line integral. All right, let's see, what is C? C is the closed curve formed by y equals 2x and y is the square root. So what I did was go down here and just draw a rough graph here. Y equals the square root of x and y equals 1/2 x. Okay, so these intersect here at the origin 0, 0, and at the point 4, 2. That's easy to mentally check here. Now we're going in the the positive direction, so you can see the direction of my little arrows here. Okay, imagine it like circulating around there. You can see that would be the positive direction there. That's what we mean by that counterclockwise direction, the positive direction. Okay, all right. So that is the boundary of R, that thing I'm calling C here. Okay, I've written that there. All right, what I'm going to do is come up here, okay? Remember, I want to go what? This is my M, is the 2xy, and my N is y squared. So to use the green theorem, I'm going to do this. Excuse me. The partial derivative with respect to x of the n, which is y squared, minus the partial derivative with respect to y of the m. Okay, so I wrote it slightly differently this time, just for variety. And you can see the first derivative is 0. The second derivative would be minus 2x. So 2x, and then we've got a minus sign. So we're integrating minus 2x over this region R. So I've got the double integral over R minus 2x dA. Okay? And we're going to go ahead, this is so weird here, we're just going to go ahead and there's no particular advantage of some sort of parameterization, or that would be, usually for the boundaries anyway. So no change of variables. We'll just stick with good old Cartesian coordinates. I went ahead and went dy then dx. Okay, you could have gone the other way. Okay, let's say we're going to go this way though. All right, dy dx. So let's see, y is going from what? The square root up to, or I'm sorry, not the square root, the line 1/2 up to the square root. So it's going from 1/2 x up to the square root. Okay, so that's going to be in the y. Okay, where's x going from and to? Okay, x is going from 0 out to 4. Okay, you could try it the other way if you want, interchanging x and y, but you should get the same answer, right? So there you understand the limits of integration here. Okay, now the first thing, we do the inner integral, right? This is an iterated integral. So we're going to integrate negative 2x dy, treating what? X like a constant, x and y independent variables here. And you can see we get what? Negative 2xy. Where's y going from and to? Y is going from 1/2 x up to the square root, or I wrote that as the half power there. And we would get what? Negative 2x to the 3/2. And then when we subtract, we would get plus x squared then, wouldn't we? Yes, minus 2x times 1/2 x. So we get the plus x squared. Well, that's pretty easy. So that's Calc 1 here. We can finish this out here using the power rule. So we would get what? Minus 4/5 x to the 5/2 when applying the power rule, plus 1/3 x cubed, going from 0 to 4. You can see it's 0. That's going to be 0. So we just have to go ahead and plug 4 in there. So I've got negative 4/5. The square root of 4 is 2, so I'm going 2 to the 5th is 32. And then 4 cubed is 64, so I've got 64 over 3. So there's what we have here. So we've got negative 128/5 plus 64 thirds. Common denominator is 15, so we go to 15ths. So we triple this guy and we get 384. And we multiply that by 5 and we will get 320. And that will give us negative 64 over 15. That is in lowest terms. So there we go. And there's the answer. Okay? Using Green's theorem. Okay? All right. Let's talk about Green's theorem and how it applies to finding areas. Okay? Okay, R is a simply connected region of R squared. What did that mean? For us, that's basically just going to mean in the plane, no holes in the region. Here's the boundary, okay, del R. Consider the following, okay? Let's just go ahead and sort of mindlessly do this. I'm just pulling this out of my hat. Let's say I was going to do this. I was going to go in the positive direction, the integral around the boundary of whatever this region looks like. Let's just say I did this. I went negative y dx plus x dy. Okay, let's say just a little problem we're going to think about. What's playing the role of my m is negative y and my n is x. Okay, so what's this going to be when I apply Green's theorem? It's going to be the double integral over the entire region R. Okay, the partial derivative of n with respect to x, so that would be the partial derivative of x with respect to x. From that, I would subtract the partial derivative of m with respect to y. So that would be the partial derivative of negative y with respect to y. And you can see that that's 1. That would be subtracting negative 1. And it boils down to 2. Okay? So this is 2 dA. Now that's a constant. I can bring it out here. Okay? So I've got 2 times the double integral of r over r of dA. Well, what is that going to be? Well, that's going to be the area of r. This is going to be the area of the region, right? The double integral over the differential area is the area. Okay, so we've got the area of r. So we've got twice the area of r is equal to what? that line integral. So we take halvesies and we've got a formula for finding the area of a region in terms of what? A line integral around its boundary. So the area of R is 1/2 of the integral in the positive direction of negative y dx plus x dy. Interesting. Okay, and we'll apply that to some problems, if not now, in the next video. Okay, let me show you another way to rewrite this, okay, or a way of rewriting it or rewriting it. Okay, the area of R is 1/2, okay, the integral here. Do you see this? This is what I'm regarding as a determinant. Okay, remember how to do that? So this is going to be what? If you evaluate this determinant, that's going to be x dy minus y dx. Okay, remember it's the product of the main diagonal elements minus the product of the off diagonal elements. And it's easy to remember this because I just go x, y. Well, that's just alphabetical. And underneath I've got what? Dx, dy following them. Okay? All right? And just do that. Okay? So that's exactly what we've got up here. Okay? Written in a slightly different way. Okay? Let's just talk about this. Just a quick, easy example here. Find the area of the circle of radius A. Okay, so the radius is A, some fixed value centered at the origin. Okay, well the area would be 1/2 the line integral around the boundary of that circle. Okay, around the boundary of the circle, x is going to be what? A cosine theta, and y is going to be A times sine theta. Now taking taking differentials, that would be what? Negative A sine theta d theta. Don't forget your d theta. You could put it outside if you want. But A cosine theta d theta. Okay, so do you see what I did here? Just coming up here and finding those differentials. Like I'm saying here, don't lose your differential d theta when you do that. Okay, let's go ahead and just work out that determinant here. And it would be what? A squared cosine squared minus negative A squared sine squared. So that's really plus A squared sine squared. Okay, so that becomes double negative becomes a positive. Yes, that's not a negative sign there. That's just a mess. Okay, you can say A squared cosine squared plus A squared sine squared is just A squared. So that's a constant, right? Since A is a constant. So I've got A squared over 1/2. The integral of d theta going from 0 to 2 pi. That's going to be 2 pi. So it's going to be 1/2 of 2 pi, which is pi, A squared. Ta-da! Okay, you didn't learn anything new, but I'm just showing you that you can actually find the area of a circle via a line integral. Okay, so that's interesting. Okay, so it's just a special case of Green's theorem. Okay, I just wanted to sort of give you a picture of what's going on here. True, we just followed through and used Green's theorem, and you can see the proof in the book here. But area in Green's theorem, just kind of a picture. Let's say I've got a little bit of the arc here coming along. Okay, so this is the boundary of some region, supposedly. I've got a point xy right here. And then I'm going to scooch over just a little bit along that that curve, and I'm going to be going in the positive direction, in other words, counterclockwise. So follow the arrows. And I'm going to say I'm at a new point, x plus delta x, y plus delta y. Okay? Now let's talk about the area of this triangle. See this thing, this little triangle here, formed by these 2 points in the origin here. I'll put an O there. In the origin. What's the area of that triangle? Well, it's about the same as the area of the sector is what I'm saying. Okay, so see how they're a little bit different here. See because this is just a chord here, right? Whereas this has a little bit of curve to it. There's going to be a little bit of a difference between the area of the actual sector and the area of the triangle. But they're approximately the same. Okay, and in fact, I would argue they're up to second order differentials, they're going to be the same, okay? But I'm not being too rigorous about the argument here. Like this curve is nice and continuous and stuff. Anyways, just get the idea here. I'm not trying to go that far here. Okay? Now, if you're going to be talking about the area of a triangle in this direction here, if you remember, you can do that with a determinant by what going 1/2 the have the two vectors here, okay? X, y, and then what? X plus delta x, y plus delta y. So I've got the two vectors right here, position vectors, and I'm going to find the determinant of that, okay? Because of the direction this is going and delta x and delta y are small, I guarantee I've only moved a little ways in the, or at least if I make delta x and delta y small enough, I only moved a little ways along that curve, so I'm definitely moving in the positive direction. I claim that these two are exactly the same. Okay, do you remember that a multiple of one row added to another row doesn't change a determinant? So I went -1 times the first row added to the second row, and I got this determinant, okay? All right, so that's the area of that little triangle. Now, what's our idea for the line integral? Well, we're going to do what? We're going to be adding up a whole bunch of these, right? We're going to break up the boundary into a whole bunch of these little things and add up a bunch of, little determinants that look like that, and take the limit as what? Delta x and delta y go to 0, and that is going to give us this in the limit, okay? So that should give you an idea why you're getting the area of the region this way, okay? 1/2 that line integral of that determinant, okay? So there's the idea. By the way, I just do want to point this out, okay? This doesn't necessarily have to do necessarily with what I have drawn above here. But when you're doing something like this, let's just draw a little line here, okay? Suppose I've got a curve here so that I don't have the origin actually interior to my region, okay? So imagine this being my region here, okay? This is my region. Notice that the origin is not interior to that, okay? But you see how I'm, traversing that region along the boundary in the positive direction. See the direction of the arrows, okay? I'm going to think of it this way. Well, I've got 2 points of tangency here, A and B. If I imagine lines from the origin, they would just be tangent to this region at points A and B, you see, okay? And I'm going to imagine this then. I'm actually integrating from A to B along what I call curve 1. So that's just this part of the curve, right? This part, all the way along to B, okay? And then C2 is another part. It's from B back to A, okay? I hope you understand what I'm saying here. All right? All right. Well, the integral all the way around C is going to be the sum of these two then, right? Okay? The integral around C1 plus the integral around C2, okay? When I integrate around C1, what I'm actually getting is the area of this figure figure O, okay? Look back at my proof up here when I was doing this thing. I would actually be getting the area of the figure OA, and then C1 coming around, B back to O. Do you see what I mean? Okay. I'd be getting, follow my trace here. See, I'd be coming around like that. I'd be getting the area of that whole thing. Okay. All right. But when I'm integrating on C2, see, I'm integrating this way from C2. It looks like what? Relative to the origin, like I'm doing what? I'm traversing in the wrong direction. Actually, when I integrate that, what I would be getting is, do you see this little negative here? Okay, I would actually be getting the negative of the area O, B, C2, A, okay? I'd be getting the negative of the area of this part, okay? Then when I combine the two, remember the areas of each of these, when I add the two, what happens is this part gets canceled out, and I'm left just with this part up here, giving the area of the region I was talking about. Okay, so I have that written right there like that. Okay? Alrighty? So this works even if the origin is not interior to the figure or the region here. Alrighty? Alright. Well, I hope you understood that and are able to work some of the problems in Green's theorem.